Okay, gang, this is a big chapter, and it's very important that you understand Chapter 6, Fire Dynamics. The objectives for this chapter: describe the components of an atom, explain how an atom becomes reactive, describe the process of combustion at the molecular level, describe three forms of matter. Explain how the process of combustion affects the different forms of matter. Identify and describe the different types of heat producing energy. Describe the four stages of the fire evolution. Identify the four classifications of fires and the principles involved in their extinguishment. Fire essentially is the rapid oxidation process that is a chemical reaction resulting in the evolution of light and heat. Fire science must analyze the chemistry, thermodynamics, and the behavior of fire. Again, essentially, in this chapter, we're going to look at, I hate using the term how fire is made, but that's kind of it in a nutshell. We're going to look how something burns and why, starting at a cellular level. So let's review. An atom is the smallest unit of a chemical element. The core of an atom is the nucleus. An atom is comprised of protons and neutrons. The protons are the positive electrical charges, and the neutrons have no electrical charge. The orbiting the nucleus are the negatively charged electrons. Electrons usually equal to the number of protons. The number of electrons in the outermost orbit determines if the element will react chemically with other elements. The inner orbit holds at most 2 electrons, except hydrogen, which has only 1. So a good way to illustrate this is using the Lewis dot model. So if you have, say, hydrogen here, it has 1 electron. And hydrogen is one of the most common elements in the world, in our environment. And hydrogen pretty much binds for everything because all elements want to have an outer shell, meaning that outer orbit of electrons to be even. Now, we all know water is made up of hydrogen and oxygen, so here's how basically it is illustrated by going together. So we have hydrogen here, and it has 1 electron in the outer shell. Oxygen actually has 6. Electrons in that outer shell. So when it bonds, hydrogen wants to bond with everybody, and all elements kind of want to have a fat, full outside outer shell. So oxygen actually has spots for 2 more hydrogen spots. So let's see, we have 2, 4, 5, 6 electrons with oxygen. So then we take our hydrogen, and he jumps on right here. And then we get another hydrogen that jumps on right there. So now we have a full outer shell of the oxygen, And now we have 2 parts hydrogen and 1 part oxygen. So that is H2O. So a little chemistry review there for you. And this just kind of goes back more to that Lewis-Dot model where the second orbit can hold a maximum of 8 electrons, third orbit 18 electrons, and oxygen has a total of 8 electrons, 2 on the innermost orbit, and the other 6 in the outer orbit. So depending on what element it is will dictate how many electrons it has. And you can look at the periodic table and it'll tell you how many electrons each element has. So because the outer orbit does not contain a full amount, oxygen will bond chemically with other elements in a process called oxidation. And molecules are formed by joining 2 or more atoms with a shared electron that form a new chemical bond, essentially a new element. So that's kind of what we did with that H2O example. As seen here, oxygen has 2 oxygen atoms. Water, H2O, has 2 hydrogen and 1 oxygen atoms. Molecules are in constant motion, always moving, and the amount of motion determines the physical state. And that's a good example. Depending on that outer shell, dictates whether you have a solid, liquid, or gas in terms of how fast those electrons are moving. So, matter is basically anything that has mass or takes up space. And matter can come in 3 different forms or states. Solid, such as the desk or the chair you're sitting at or chair you're sitting on. Liquid, and of course, gases. Kind of interesting, when we look at water, you can very easily see it in all 3 states. Water can be a liquid that we drink all the time. You get water cold enough, then it turns into a solid. And of course, you get the water hot enough, and it turns into a gas. When water is the most dense at its, ice stage, then those electrons are basically not moving as fast or not as excited as when they're in the gaseous state. So, solid matter, the molecules are so close that they cannot change places. The free movement is not possible, and the molecules only vibrate in place. The form and shape maintained until a reactive force breaks the molecular bond. The oxidation process is an exothermic reaction, and this is a key word. So exothermic means that it is giving off heat. So when oxygen binds with something, like in the case of iron, and produces rust, as that rust is producing or getting made, it is releasing heat or energy, and that is an exothermic reaction. The iron is an example of a chemical chain reaction. And an actual fire being released or something burning, we'll go more into this later, is an example of the self-sustained combustion, meaning fire and its burning. So what is actually burning? And let's look at wood. Wood is composed of cellulose. As the surface temperature of the wood increases to 212 degrees Fahrenheit, the moisture in the wood begins to boil and converts to steam. When the surface temperature of that wood reaches 482 degrees Fahrenheit, the wood begins to go through a process called pyrolysis. And pyrolysis occurs at different temperatures for all objects, whether it's wood, brick, glass, lead, whatever the case may be. And what that basically means is that element now is being acted upon by the heat, that energy. Remember, energy can only transfer form, but it's beginning to change it into a gas. And that gas, from that broken down element, that piece of wood, is actually what is burning. It is the gas being given off by the wood breaking down because of the application of heat. And as that gas burns, it produces more heat, which continues that combustion process, that reaction, releasing more gas until eventually the fuel is gone. So just some food for thought. The solid matter takes a lot more heat than a liquid matter. And then, of course, if something is flammable and in the gaseous state, it takes the minimalist amount of heat or energy. And that's when you get just that little spark, and such in the case of dealing with natural gas or gasoline fumes. So now the liquid matter is in a liquid state. Its molecules are in proximity to one another, and they are free to move in all directions. Liquid always assumes the shape of the container in which it is confined. The speed of the molecule is directly related to the temperature of the liquid. So again, the colder it is, the more slow it's going to get. The hotter you get that water temperature-wise, the faster it's going to get till it gets to that state of 212 degrees where the water begins to boil and then starts converting into steam. But again, that takes a lot of energy. So as we're talking about turning into steam, we got to talk about vapor pressure of a liquid in a closed container. And that is when the equilibrium is reached. As the temperature increases, the molecular movement will increase and the vapor pressure will increase proportionally. So a good way to look at this is, let's say you have a container, a cylinder container that is filled with water, and this container is closed. Well, it will hold a certain amount of air and water in there, right? But as that water begins to heat up because you start applying, say, torches to it, that water is going to start converting from a liquid to a gas. And because it's turning to gas, it takes up more space and begins to spread out. Unfortunately, that steel container we have can only hold so much pressure until, of course, it'll explode and levy. But that's a good example of that vapor pressure. So it's kind of like a bottle of Coke, 2-liter bottle of Coke, Pepsi, 7-Up, Sprite, name your poison, and you shake it up, right? Well, when you crack that lid, that vapor pressure is released. And if you ever had a Coke can that you left in your car on a real hot summer day, what happens to it? The ends begin to blow out or bubble out because of that increase in pressure, and that is vapor pressure, until either A, the can ruptures or the temperature goes down and that gas starts turning back into a liquid. So when the vapor pressure of the liquid equals atmospheric pressure, the liquid will boil. And it will continue to boil until all the liquid is converted into that vapor or gas. Liquid matter does not burn, just like a solid matter does not burn. It is when that matter is turned into that gaseous state that it will actually create that flammable atmosphere. Gasoline has a vapor pressure range of 7 to 14.5 psi and can generate flammable vapors at as low as -4 degrees Fahrenheit, which is its flash point. So everything has its own individual flash point where it starts giving off that gas, and then you mix the gas with the oxygen, that oxidizer, and all you need now is that spark, and you have combustion. Ignition temperature, or fire point, a temperature at which the liquid will emit vapors at a rate that will support a flame after the ignition source is removed. So that's basically saying diesel fuel, okay? If you take a match and you toss it into a open container diesel fuel, it will not light because it has not reached its flash point. However, you begin to heat that diesel fuel up and eventually it will begin to burn. And then you can take away that ignition source, that torch or say matches or whatever the case may be, and it will continue to burn because it has got to that ignition temperature or fire point, because now the fire is producing enough heat to change that liquid into a gas. And that all depends on, of course, what the product is. I'm hoping that makes sense. Atmospheric pressure at sea level is 14.7 psi, and that's a constant. If the vapor pressure of a liquid is above 14.7 psi, it can only exist as a liquid when confined in a vessel or when the temperature is lowered. Excuse me. An excellent example of this is propane. For example, the propane that powers your grill. That propane in that tank is under pressure, so it exhibits a liquid state. When it gets opened up to the air outside, that liquid turns into a gas, and that's the gas that's in your grill that burns. But as long as it's in that confined space under pressure, then it is in a liquid state. For propane to be a liquid at normal atmospheric pressure, the temperature would need to be -20 degrees Fahrenheit. At that temperature, the vapor pressure would be 11.5 psi. Gaseous matter. In this state, molecules move at high speeds. Substances in this state occupies more space than if a solid or a liquid. So vapor density is determined by the substance molecular weight compared to that of normal air. So now we're basically taking gas and we're weighing it against air. If the vapor density is greater than 1, meaning air, the gas will sink to lower levels, as illustrated here. If it is less than 1, then it will rise up to the atmosphere. So here's the lovely mathematical formula on how they get that vapor density. It's the molecular weight of the gas or vapor, divide that by 29. And again, you can find that off the periodic table, but I'm not expecting you for this class to know anything like that. This is just more for your information. Now, once you get into the chemistry of hazardous material, then yeah, you have to know some of this stuff. The behavior cannot be predicted when the same substance, however, is a liquid instead of using gas. Now, in the liquid state, instead of comparing it to air, we're going to compare it to water, and that's referred to as the specific gravity. So again, it's similar, but your measurement tool is not air, but water, and that's known as specific gravity. So if something is lighter than 1, then it is going to float on water. If it's heavier than 1, then it will sink. Gasoline has a specific gravity of 0.72, which is lighter or less than 1. So gasoline and oil, so to speak, will float on water. Hence, one of the problems you have trying to put out certain flammable liquids like gasoline with water, because the material will just float on top. So you have to use other means than water to put them out, or in addition to. But we'll go more into that later. Here's a great illustration of oil. You have a container of water, and you take just some regular cooking oil or motor oil, and it will float on top. So why should firefighters be concerned with the form of matter with which they are faced on the emergency scene? Food for thought. Energy is defined as the capacity or the ability to work. And it can exist, and this is energy now, as either potential or kinetic energy. And potential energy is meaning it's in a state that has the ability to do work. And kinetic energy is when it's actually in movement. So, for example, you take a book and you place it on the table. That book contains potential energy. You push that book off the table, it begins to fall, and that's an example of like kinetic energy. Or you take a match to that book and you begin to heat it up, and it begins to burn, then it's releasing that energy in the form of heat and light, and then of course some leftover water vapor. Energy can exist in many forms, and remember, energy cannot be created or destroyed, only transfer form. So it can exist as heat, light, electrical energy, mechanical energy, nuclear, or chemical. So an example of heat would be the sun. That is energy that is radiating from the sun, heating the earth. Light from a flame. That is an example of the energy being illuminated. Of course, electrical and power, mechanical, such as your car, nuclear reactor, and even chemical, such as chemical reactions. For example, when you take powdered chlorine and you mix it with hydraulic fluid, that is an exothermic reaction that's going to occur, and it's going to produce large amounts of heat and will eventually get to a state where it will produce a flame. The most common source of fire encountered by firefighters is in that electrical, mechanical, and chemical states. The way they measure that energy release is known as BTUs, or British thermal units, in the Fahrenheit scale. And then the Rankine scale is the metric system, which is done in kelvins. The Fahrenheit scale A degree is 1/180th difference between the melting point of ice and the boiling point of water. Water freezes at 30 degrees Fahrenheit and boils at 212 degrees. And basically it's just measuring how much energy it takes to change that temperature 1 degree. BTU, 1 pound of water by 1 degree Fahrenheit. Two concepts of heat energy: specific heat and latent heat. Specific heat is the amount of heat a substance will absorb as the temperature increases. For example, water. Water will absorb lots of energy, hence why it's a good extinguishing agent. And latent heat is the amount of heat absorbed by a substance when it changes the physical state without changing in temperature. So water will have a large amounts of specific heat that it'll absorb up to that 212 degrees. And then after that 212 degrees, it's taking a lot more energy to change it to a gas, and that's that latent heat phase. And here's some common measurements for you. Latent heat of fusion, basically melting, 143.4 BTUs of latent heat is needed to convert 1 pound of 30 degrees Fahrenheit ice to water. The latent heat of vaporization, and notice the difference between fusion and vaporization, melting and boiling, is 970.3 BTUs of latent heat is needed to convert 212 degrees Fahrenheit water to 212 degrees of steam. So that's what I was talking about earlier. Look at all that energy that is required to change water from that liquid state into steam. So again, a flame is energy. Energy cannot be created or destroyed, only change form. So now that flame is changing from a flame, fire, into steam. And then of course that steam is heat, and that steam dissipates throughout the atmosphere. So how does that heat move? And heat, again, as I said, is energy, and it moves in 3 different ways: conduction, convection, and radiation. Conduction is the ability of heat to move through matter. The heat conductivity of matter is directly related to its density. All right, so let's put that in English. You have a metal rod, or a metal coat hanger, if you will. You heat up one side of that coat hanger. You stick it in a fire because you're roasting marshmallows or cooking hot dogs. That other end, that coat hanger, will eventually get hot. And that is because the energy or heat is getting transferred from the fire to that coat hanger in the form of conduction. So that heat is moving from that tip to the other end. And the heavier, the more dense the object is, the better conductor of heat it is. So iron is very dense, very heavy. So that's why you have cast iron skillets, because it is a great conductor of heat. The ability of matter to dissipate heat is directly related to its density. Metals have higher conductivity, which we talked about. And we need to understand that heat sinks and falling is a possibility. Now, what we mean by dissipate heat is how that heat is transferred in certain objects. And we talked about conduction and in terms of that metal as an example. Another example, of course, could be that fire in the fireplace or in a room, and it's gonna, rise up and then eventually sink down. Spalling is the process of concrete. When you heat concrete up, that gas, or I should say water vapor that's locked in the concrete, will turn to a gas and cause it to kind of explode and free out. And here's our great picture of our cast iron skillet with conduction, and the butter is melting because the energy transfer from the stove going through the skillet to the butter. Convection is another process, kind of like your convection ovens, but the heat transferred by convection usually occurs in a gaseous or liquid state. Heated gases follow the path of least resistance, such as burgle openings. So a good example of this, if you look at the fire behavior video in this week's lesson in Blackboard, you will see how the tree catches fire. It starts running up the tree and then hitting the ceiling, and then the entire ceiling starts getting engulfed because that heat is now going up to the ceiling and getting spread across, and it is chasing the oxygen, which has an air current, and you can see that air current move past that bunny at the bottom. Example of a chimney as a fireplace. Convection is the transfer of heat through circulating air or liquid. Your convection oven are another great example, since we were talking about cooking earlier with conduction. Finally, you have radiation. We talked a little bit about heat transfer from the sun, and basically radiation, the transfer does not require direct contact with the heat source or with conductive heat currents. Radiation energy transmitted as electromagnetic waves in the form of infrared rays. So again, the prime example is the sun. Another example of heat transfer probably that way would be your microwave oven. So, in this day and age, we've got to measure everything. So one thing they consider is the heat of combustion, or caloric value, and that is the amount of heat or energy a substance releases during the combustion process. Calculations of heat of combustion is based on, and I can pronounce this, stoichiometric. Dictionary.com does a great job pronouncing it for you, or complete combustion reactions. And that basically means that you have your fire load, and that is whatever is burning. The caloric value is measured in joules over grams. And the rule of thumb estimated to measure caloric value is this. If a substance is cotton, wood, or paper, and that's what we call ordinary combustibles, it will release about 8,000 BTUs of energy per pound. And look at your grills. That's a good example of the BTUs. That's how much, of course, heat and energy it releases during the cooking process. The more it releases, the hotter it's going to get, or the more it can cook. Now, if a substance is plastic or hydrocarbon, meaning oil, petroleum-based, it is 16,000 BTU per pound. So you take a pound of cotton versus, say, a pound of some sort of plastic, which is going to burn hotter? And the answer is your plastics, those hydrocarbons. And we look at everything in our homes today, they are comprised of primarily petroleum products. We've kind of gotten away from the cotton, wood, and paper stuff, and everything is in synthetic or plastic because, it's cheaper. But it's going to burn a whole lot hotter and a whole lot quicker. So fire flow, or critical flow, is a computation And what you're basically looking at is the BTUs 1 gallon of water will absorb. And that's done by calculating the fire load. You divide the fire load by the number of BTUs, and that'll kind of give you a guesstimation. In short, what you're trying to figure out is how much water you're going to need to put something out that is on fire. And that's where all this is going. Now, things will burn differently depending on what form it is in. And what we're talking about here is that rate of heat release. So we know that 1 pound of wood is going to burn, and it's going to release 8,000 BTUs of energy. Now, the question is, how quick will it release that 8,000 BTUs? And that goes into what form it is in. Because we already know that wood or anything that burns has to be in a gaseous state. So you take a 1 pound block of wood and a 1 pound of sawdust or wood chips, which one will burn slower? And the answer is going to be that 1 pound of solid block wood, because that wood is more dense than that shaved sawdust or wood chips. There's more surface area in the wood chips to begin absorbing that heat and turning over a lot quicker into gas through that process known as pyrolysis. Now, something to keep in mind is something called spontaneous heating. And that occurs when a substance increases in temperature without any assistance of an outside ignition source. Because we were just talking about, say, you have a pound of wood and a pound of sawdust. You apply heat, fire to them. Which one's going to burn quicker? And that's going to be the sawdust, because it has more surface area and it's easier, it's lighter, it's less dense, and it'll turn into a gas quicker. Now, something that burns that will do it automatically without applying heat is referred to something that burns spontaneously or spontaneous heating. When the heat energy is generated faster than it can dissipate through normal means, ignition or spontaneous ignition will occur. So you take a hay bale, and hay bales will spontaneously combust, because when you cut the hay, they roll it up. Notice they leave it in the pasture, right? Well, they're doing that because that hay bale is beginning to break down, and as it decomposes, it's going to release heat. And if there's not enough circulation or air around it to cool that bale down, it will heat up enough to cause more of the product to start going through pyrolysis, and eventually the temperature will get to a certain point where it will auto-ignite. And now you've got a fire. So that heat of decomposition that we just kind of talked about is considered an endothermic reaction. An endothermic reaction is something that is taking in heat, where an exothermic reaction is giving off heat. Heat of a solution. Heat release is released when a substance is dissolved in a liquid. Reaction can be endothermic or exothermic. And again, endothermic is absorbing heat and becomes cool, and an exothermic is releasing heat. So that's kind of like an exothermic reaction would be water turning into a gas as it boils, and an endothermic reaction would be energy applied to water, cooling it down and turning it into a solid, such as ice. Heat release when a substance comes in contact with a liquid or with air. This type of reaction is capable of causing ignition. Water reactive substances are classified as hydrophoric materials. Pyrophoric materials are substances that spontaneously react when exposed to air. So let's look at electricity now. The passing of electrons from one atom to another. All atoms want to be balanced, as we talked a little bit about with the electrons in the Lewis dot model. Positively charged atoms have a strong attraction for negatively charged atoms and vice versa. The attraction is called the charge. When electrons move through matter, the movement is called a current. The matter is called the conductor. Basically, what is that current going through? Now, there are 6 forms of electrical heat energy, and that is resistance, arcing, sparking, static, lightning, and induction. Resistance, the opposition a substance offers to the passage of an electrical current. For example, your insulators. Rubber, glass, and dry air have high resistant qualities, where water has low, or metal has low resistant qualities, meaning that it's more of a good conductor of electricity. Such as copper, silver, aluminum, and steel are excellent conductors, and the amount of resistance in a conductor depends on its thickness and length in relation to the current. Resistant heating, used for cooking and heating homes, is a great example. And that's like looking at the elements. You know, you turn on the stove, you see those bright red elements. That's resistant heating. Or maybe you have a little space heater, and again, you turn it on, you'll see that red hot element, and then the fan blows over, blowing the heat out in the room. Another form was the arcing, and it is caused when an electrical current is interrupted, and it can be intentional or accidental. A great example is when you turn a switch on and off. You will have some arcing occurred, or sparking. And you can see that if you turn the lights off and you will kind of watch the switch. Sparking is different from arcing. It is a short-term, one-time event. High voltage discharge with low energy output. Normally not capable of causing ignition. And it is, however, dangerous in flammable atmospheres. So an example of sparking would be your grill with that push button start. You know, you open up your grill top, you turn on your propane tank. We already know the propane tank is in that liquid form. When we open up the discharge, the liquid changes pressure and turns to a gas, and now you have this flammable environment because you got oxygen in there, you got this fuel in a gaseous state, and now it's just waiting on that spark. And you hit the button and you get that quick spark, and voila, now you have flame. And that flame will continue to go as long as you have fuel and oxygen. Static electricity, as I hope we're all familiar with. You know, you get those nice wool socks, where the case may be. You go dragging your feet through the carpet on a nice winter day. Now, the air is very dry, and you ended up touching something that's a different charge, and you get that shock. And that's kind of like one of the debates about static electricity. Well, static electricity causes gasoline to ignite at the fuel pump. And you know, they have those warning labels at the pump to touch something metal before you handle the pump and all that kind of stuff, and vice versa. And I think Mythbusters, if I'm not mistaken, though I haven't seen the episode, did something on that. And if I remember correctly from what I heard, they couldn't get static electricity to ignite gasoline vapors. But anyway, in case you're ever on Jeopardy or you find it, let me know. Lightning, as such as from static electricity or in the environment, basically you have electrons jumping into the ground as large static sparks. And of course that is energy. It hits anything, you're going to have that transfer energy and heat. Induction. If a conductor is subjected to an alternating magnetic field, a flow of current is produced. As the frequency of alternating magnetic fields increase, the flow of the current increases and produces resistance and heating. And this is just a fancy way of saying microwave oven. That's how a microwave oven works. Induction. Friction is another great way that produces heat in the form of mechanical energy. And that's when two solids are rubbed together. So let's think about it. You have a car. That car is, of course, powered by a combustion engine, gasoline powered. So that gasoline turns to energy in the form of movement in the car, causing things to move. Well, now that car is moving, it's technically producing energy, right? Well, that energy needs to change form from the process of movement to something else. Because, hey, look, there's a stop sign. So how does that energy transfer form? And that is done through the process of friction in terms of the brake pads. The drums, which are behind the wheels, have another piece of metal or metal type stuff that presses against it, causing friction. So that friction is producing heat, and that heat is coming from the energy of the movement of the car. And now that movement is slowing down because it is losing energy, because that energy is changing from movement to heat. So hope that makes a little sense in terms of friction. And that friction, of course, produces the heat, and the heat is dissipated in the environment. And on so it goes. Compression is another form of mechanical energy, and that occurs when a gas is compressed suddenly. And your examples is a diesel engine, or refilling an SCBA cylinder too fast. So that's kind of interesting. If you have your self-contained breathing apparatus that we talked about in the other chapter, and it's full of air, you put air in that cylinder and you do it quickly, it's going to get really hot. And that's because of the compression. Now, you breathe that air out really quick as well, and it's going to be an endothermic reaction, and it's going to turn it into ice cold. The combustion process has two types, type 1 and type 2, or flaming combustion and non-flaming combustion. The type 1 combustion process is charcoal, that non-flaming. Again, type 2, illustrated here as your regular campfire, is flaming. So let's try to bring this all full circle. In order for something to burn where you have fire, all elements of the fire tetrahedron need to be present. You need to have a fuel. You need to have heat. You need to have oxygen and a self-sustaining chemical chain reaction. remove any one of those and the fire will go out. So for example, fuel would be wood. You apply heat to that wood, it goes through pyrolysis and begins breaking the wood down and turning it into a gaseous state. You take that gas, you mix it with oxygen, you get it at the right level, and then you have that spark or arc. It will continue to burn as long as the fuel is present, and that's that self-sustaining chemical chain reaction. Here is an illustration of the fire tetrahedron: oxygen, heat, fuel, and the chain reaction. Again, removing any one of those parts, the fire will go out. Now let's look at the burning process, and you can kind of watch this in the video, which makes a little more sense. But you have 4 stages. You have the ignition stage, you have the growth stage, you have the rollover, you have also known as flashover, and then you have fully developed and decay. So ignition, growth, fully development, and decay are the 4 stages, and the growthing stage has 2 subcategories in terms of rollover and flashover. The ignition stage is when it's just beginning to burn. It's a very incipient or small fire. Growth, more product is being burned because the heating from that initial fire is causing the surrounding material to begin to off-gassing and continue to burn. Then you have the fully development stage when everything is being consumed. And then the decay stage is when it begins to go down and the fuel is consumed. So the fire begins reducing in size. Now, one thing I want to go back and talk about, that flashover, and you see the video on it, that is during the growth phase or fully involved, and that's when all the product, all the fuel, begins off-gassing at the same time, because that small confined room is so full of heat that everything starts giving off that fuel in the pyrolysis state, and then it ignites spontaneously because you got all that super gas, we got plenty of oxygen there, and you've got that fire going, and then poof, you'll get a flash where basically in a blink of an eye everything is burning around you. Not a good place to be. So let's look at our different classifications of fire. And fire is broken down in different classes, and that basically depends on the fuel. So Class A is what we call our ordinary combustibles, such as wood, paper, and plastics. We put those out primarily with water. Class B are your flammable liquids, and that's your oils, gasoline, and kerosene. Now, if we remember correctly, water and oil. The oil and gasoline have a weight that is less than 1. So water will actually go underneath it, and those oils will float on top, continuing to burn. So you need something other than just water. And the example being here is a dry chemical agent such as an ABC extinguisher or some sort of foam like the Dawn detergent. And that acts as a smothering agent that prevents oxygen from getting to that fuel and that gasoline, so you don't take away that oxidizer component, thus causing the fire to go out. Your Class C is your electrical fires. If a fire continues to burn, it's going to be an A or B, but usually it's kind of that source is the electricity. And when something is an electrical fire, it's a Class C, and the means of extinguishment is removing the current or turning off the power to it, switching a breaker, getting the power company to shut the line down. After that, then if anything is still burning, then it's usually just a Class A or B fire. Class D is your metals. Believe it or not, certain metals will burn. For example, magnesium. Magnesium will burn. You look at the sparklers that you play with on New Year's Eve and 4th of July, that's an example of magnesium. Now, in order to put out a flammable metal, either A, you need large, copious amounts of water to put it out in relation to the amount of product. So you just have a little bit of magnesium on those sparklers, so if you drop it in water, a large cup of water, it will go out. However, if it was a large bit, like say an engine block, you would need, again, large amounts of water, or you would need some sort of dry powder extinguishing agent, like a dry chemical, to break up that self-sustaining chemical reaction in order to make the fire go out. Finally, you have the Class K fire, and that's relatively new in the terms of the classification compared to the other ones, and that's basically your cooking oils. And they decided to break it off from your flammable liquids and make its own separate category because it has some very unique features. With your Class K or oil fires, you can basically add those certain extinguishing agents and you can turn it into like an emulsifier or basically like a soap form to put the fire out. So this has been a lot to go over, guys. So I really need to make sure that you read it, you understand it, ask me plenty of questions if you need to. Watch the videos. They reiterate this and show it in a little different way. So let's recap. A knowledge of chemistry and physics of fire is vital. If you understand why something is burning, then you can put it out. Okay? That's the importance. That's why you need to know this. Heat is transferred by 3 methods: conduction, convection, and radiation. Energy cannot be created or destroyed. It can only change form. Firefighters commonly encounter chemical energy in the form of an oxidation reaction. There are 6 forms of electrical energy: resistance, arcing, sparking, static, lightning, and induction. There are 2 types of mechanical energy: compression and friction. There are 2 types of combustion: flammable combustion and non-flammable, such as flaming combustion, I should say flame and no flame. That's your type 1 and 2, like charcoal grill or wood burning. There are 4 stages total of the fire. You have the ignition, where it's an incipient. Then you have the growth. Then you have the fully developed, where all the fuel is burning spontaneously. In that developed stage, you have, that flashover stage, or point, I should say. And then you have the decay, where everything is consumed and now the fire reduces in size. Remember the different types of fire classification: A, B, C, D, and K. And what methods are used to extinguish each. So again, if you have any questions, you can email me at aroberts@athenstech.edu. You can call me at 706-357-0162, or you can look at the calendar in Blackboard and we can chat during virtual office hours on a one-on-one type basis or in a group, depending on how many people show up. Until next time, you guys have a wonderful day.